So let's take a look at some examples of code corresponding to these different types of pointer arithmetic, right. So what I have done over here is I have declared an array int a of 10 and I am using this notation in order to initialize the values in a, right. So what this basically means is that because I have given all the values 1, 2, 3, 4 up to 10, what happens is a of 0 will take the value 1, a of 1 will take the value 2 and so on up to a of 9 which will have the value 10, and in fact we can see what that looks like. Now what I have done over here is I have printed out exactly the same value using two different notations. One of them is using the a of I notation. As I said, the square brackets indicate the of operator or the array access operator, and a of I should give me the ith element in A. Now supposedly by that same token the star a plus I should also give me exactly the same thing, and interestingly enough what I should actually see over here is that a is some address location and star of a plus I should give me an address location which is I elements into the future or into the array, and star of that should give me the same content. So let's run it and see what happens. As you can see, it basically says a of 0 is equal to 1 and star a plus 0 is also equal to 1, right. After all, that is what I am doing, star of a plus %d, I print the I over there and I use star of a plus I in order to get that value. So clearly you can see that a of 1 and star of a plus 1 are the same, a of 9 star of a plus 9 are the same, right. We can actually go one step further than this and we can look at the addresses themselves, right. Let us take a look at that. What I am going to do is, rather than printing out the values over here, I am going to actually print out the star a of I, and I will also just print out a plus I out here. Now you might note that there are these orange squiggly brackets that come up over here, and it in fact gives you a kind of a warning, right. So the orange squiggly lines that come up in Replit, right, and in many other code editors that you might be used to, is a warning, it is not an error, right. So it is going to compile, it is going to go ahead, and it's actually what it's telling you is a very useful error, it's something to a useful warning, it's something to keep in mind, right. What it's telling you is that when you take ampersand a of I, that actually becomes a pointer, right. A of I is the dereferencing operation, it is taking the ith element of the array A, but the ampersand operator is actually taking the address of the ith element of A, right, which means it is a pointer that comes out as the result. And when you do something like that and then you try to print it out as %d, the compiler is giving you a warning saying that look, you have something which is a pointer, you are trying to print it out as an integer, are you sure this is what you want to do, right. In our case it is fine, we know that this is what we expect, so let us try and print it out, right, run this. And you can see that sure enough a of 0 now comes out with a number. I do not know why it gave this number, in fact let us run it again and you will see that the numbers have changed, right. Every time you run this the numbers are going to be different, sometimes the numbers end up being negative, right. Now why are they negative? It is not that the address is negative, the address is a large 64-bit value. What is being printed here is just the bottom 32 bits of that, because it sort of implicitly takes out the bottom 32 bits when you try taking a 8-byte value and printing it out as a 4-byte value. And it is possible that because you tried to interpret it as an integer, the most significant bit was a 1, it thought this was 2's complement notation and it interpreted it as a negative number, right. That does not mean addresses are negative, addresses are numbers, they are positive numbers, whole numbers, right, between 0 to whatever capacity, right. Actually not whatever capacity, for a 64-bit address it would mean up to 2 power 64 minus 1, right, because they are supposed to be unsigned long integers. Now in practice of course what happens is that you have some number that is coming out over there and it is being printed out since the compiler is trying to interpret it as an integer. So bottom line is we do not really care about the exact value over here, as you can see every time you run it that number kind of changes, right. What is important is go from a of 0 to A of 1, and you find that this last part of it has increased by 4 bytes, which is exactly what we expect to see for an integer. And interestingly, the A plus I has also gone up by 4, right? The 60 became 64. After that, A of 2, it becomes 68, whether you go as address of A of I or just do A plus I. Both of those give you exactly the same value out here, right? So, in other words, what it is telling you is that this A of I notation and the star of A plus I notation that you have over here are not just equivalent in some way, they are doing exactly the same thing. In fact, if you go down to the assembly language, there is a good chance that depending on the compiler, most likely you will find that both of them generate exactly the same code. Okay. So, any differences that we see over there are purely something from the interpretation, from the human being's way of looking at it and understanding what the code is about. Alright, this next example that I have over here corresponds to casting, right, where we take an integer of or a pointer of a certain type and try to interpret it as a pointer of another type. So, what I have done over here is I have declared int a of 10, right. So, a is an array, but what that means is it is also a pointer, right, because after all the name a is an alias for a pointer to the 0th location of the array, right. So, keep that in mind, an array and a pointer are very closely related, they are not exactly the same thing because of differences in the notation that we use, but for all practical purposes the way that they are used remains exactly the same, right. So, a of 10 has been declared as an array of integers and it has been initialized in this way to these different values, right. Now, what I have done is I have declared a char star b, right, not short star, in this case I just decided to go with char star, and what I have done is I have taken the address a and I am telling the compiler from this point onwards treat it as a char pointer, right, and assign that pointer value, that memory location address, to b, which is after all of type char pointer, right. So, b is of the correct data type, it is capable of holding a pointer to character. What I have done is the address of pointed to by a, right, I am taking that, treating it as a char pointer and assigning that to b, okay. And what I am going to do actually over here is I know that a has only 10 elements, but because an integer is 4 bytes, I know that that corresponds to 40 characters. So, what I am going to do is I am going to actually print out all of those values and it is going to basically say b of 0, b of 1, b of 2 and so on, all the values that are present out there. Let us see what happens when I run this. So, let us see what happens when I run this function. I have to go up a little bit, but yeah, now you can see b of 0 corresponds to 1, b of 1 corresponds to 0, b of 2 corresponds to 0, b of 3 corresponds to 0. Now, how do we interpret this, right? It may help to sort of go back and look at this in terms of a memory diagram, right. Basically, what we are trying to say over here is since it more or less corresponds to this particular example that we have over here, I will just use this. I have a of 0 pointing to some location out here, a of 1 corresponds to this location out here, a of 2 corresponds to this location out here and so on. What I have done is I have made b of 0 point to exactly the same location. And then we have b of 1, b of 2, b of 3, so that b of 4 points to the same location as a of 1, right. Now, let us look at what happens if a of 0 has the value 1. This actually corresponds to the hexadecimal value 0 0 0 0 0 0 0 1, right. After all, there are 4 bytes present over here, right. And now comes the question, which byte goes where? Remember that this is running on an x86 processor, right. Replit usually uses x86 based machines, and as a result what we end up seeing is this goes, it's going to basically take the value 0 0 0 0 0 0 and 0 1 out here, right, from top to bottom, right. This is the most significant byte and this is the least significant byte. The most significant byte goes into the highest address and the least significant byte goes into the lowest address, right, which means that B of 0 will now have the value 0, B of 1 will have the value 0, B of 2 will have the value 0 and B of 3, no sorry, let me just correct that, sorry. B of 0 has this value out here, right, which is 1, B of 1, B of 2, B of 3 have the values 0 corresponding to the order in which the bytes have been stored. And that is exactly what we see out here as well, right. B of 0 in other words has this value 1, B of 1, B of 2 and B of 3 have the values 0. Now B of 4 corresponds to A of 1, the least significant byte of A of 1. As we can imagine, it has the value 2 in it, right, and B of 5, B of 6, B of 7 are the upper bytes of A of 1 which are all having the value 0. B of 8 once again has the least significant byte of A of 2 which has the value 3 and then 0 0 0 and so on, right. So you can clearly see that what has happened as a result of this casting is that I declared an integer array, I initialized it with certain values and then tried accessing them, accessing those memory locations using a char pointer. It did not complain, it is a perfectly valid memory access, and what it gives me is a very clear map of how the data actually got stored in the memory, right. So playing around with some of these pointer casts and so on can be a very useful way of understanding exactly how memory gets laid out and can help a lot with how you understand how pointers work in C. I would encourage you to try it out on your own, right. Try variants of these codes and see where the code goes and sits in different parts of the memory. Now when we talked about how arrays are located in memory, we also saw that there could potentially be this capability that the location of one array and the location of another array end up being very close to each other, right. So let's sort of see whether that's actually the case, right. What I have done is I have declared two arrays A and B out here, right, and I have initialized them to certain values, and what I am doing out here is I am first just printing out the values that are present in A of I, B of I, that is okay, that is just to make sure that we are able to access them. What is interesting here though is I am actually taking the addresses, right. So ampersand A of I and ampersand B of I do an explicit typecasting to unsigned long over here so that that warning message does not come through in the compiler, and print it out. I could have omitted the unsigned long, it would have given me a warning message, but it's always good to write your code in such a way that you do not have warnings. And ideally any code that you write, you should know exactly why warnings are there. Errors of course you cannot proceed, right. The compiler won't let you go beyond that, it won't let you run your code. Warnings, it will still let you run your code and there is a good chance that what you are getting is wrong. So do not get into the habit of ignoring warnings. As far as possible, try and eliminate the warnings by fixing whatever it is in your code that led to that warning. In this case it is very simple, right. If I did not have this unsigned long over here, I would see a warning, right. You can see that this immediately changed into this orange squiggly line saying format specified type unsigned long, but the argument has type int star, right. But when I put that back in, that warning goes away. So as far as possible, try and get rid of such warnings. So let's try and run this and see what happens. So as you can see over here, right, A of 0, B of 0, it prints out the values, right, A of 1, B of 1, so 1, 2, 3, 4 for A, 5, 6, 7, 8 for B. Now let's look at the addresses, right. What has happened over here is, it's a very long number. I printed it out in decimal so that it's a bit easier for us to understand as numbers, but what that means is it also throws in a lot of extra digits that are hard to make sense of. What we really care about are probably only the last 3 or at most 4 digits, right, because we are dealing with small arrays over here. Maybe they have, in this case, each of them has 16 bytes in it. It's not a very big array. Now this is interesting, let us look at it though, right. Look at the last 4 digits out here. The address of A of 0 is 2096, the address of B of 0 is 2080, okay. The address of A of 1 is 2100, the address of B of 1 is 2084, this is 2104, 2088, 2108 and 2092. Let us try and understand these numbers a little better. So what I have got over here is the set of numbers that were printed out by running the program, right. And what we can see is clearly we are primarily interested in the last 4 digits of these addresses, right. Everything else is pretty much identical, so we do not really care about anything else, right. So let us just focus on this part, right. And what this is telling us is that address of A of 0, this corresponds to the location 2096 and this corresponds to 2080, right. What is the difference between these? It is 16 bytes or 4 ints, right. So let us draw what this looks like in terms of memory. Basically what this is telling us is this is location 2080 and this corresponds to B of 0. 4 bytes later 2084 I have B of 1. Another 4 bytes later at 2088 I have B of 2. Another 4 bytes later 2092 and I have B of 3. Now what that means is B of 0 corresponds to these 4 bytes, B of 1 corresponds to these 4, B of 2 corresponds to these 4 and B of 3 corresponds to these 4. I can then switch over and I have address location 2096 and this corresponds to A of 0 and I have 4 bytes corresponding to that, followed by 2100 which is A of 1, 2104 as A of 2 and 2108 as A of 3, right. So you can clearly see that what has ended up happening out here is that this corresponded to the int A of 4 and this part corresponded to the int B of 4. So what looks like it has happened is my original declaration had int A of 4 followed by int B of 4, and what has happened over here is that the memory allocation started at a high address location and went downwards, but at the same time it is not that it started at the high location and then just started decrementing things. It actually picked up a value of A of 0 after going down by 16 bytes, enough to store the entire array A. After that, so in other words A starts from here and then goes up to this point, then you jump down to B of 0 which is at this point and then it grows up to this point, right. So there is a lot of jumping back and forth that you can imagine is happening out here in terms of how the memory address locations are found, right. For the most part, like I said, you do not need to worry about them. Ideally you should not even be thinking about them, for the simple reason that if you rely on the fact that in terms of memory locations A is at a higher memory address than B, when you switch over to an ARM based processor for example, you will go wrong and your code will not work the way that you expect, right. What does happen as a result of this though is that how array bounds are treated, right, and what happens when you try accessing different memory locations does change. Let us take a look at that. So what I have got over here is the same you still have this part with the code, so I am going to just comment out this part where it prints out the addresses of the code, or we can leave it there, it does not matter, right, because after all it's good to sort of see the addresses, because like I said, every time you run the code the addresses themselves are going to change. But now the interesting thing is I am going to print out with the second for loop out here runs from 0 to 8, not from 0 to 4. Remember, there are only 4 elements in A and 4 elements in B. But what I am trying to do is to print out B of 0, B of 1, B of 2 all the way up to B of 7. Right. Let us think about what that means. Right. If I go back to this picture, what I actually see is this point is B of 3, B of 4 will most likely correspond to this point out here. Right. I have actually gone outside the bounds of the array that I have, and I am going into something else that I should not be allowed to access. Let us verify that that is in fact the case, right, and then think about what that implies for how we are actually accessing memory. So what you can see is, once again the addresses you have over here, B of 0 is 16 bytes less than A of 0, right. B of 0 has the value 5, B of 1 has the value 6, B of 2 has the value 7, B of 3 has the value 8, B of 4 has the value 1. Why is that? Because it is basically picked up the value in A of 0. B of 5 has the value 2, B of 6 has the value 3, B of 7 has the value 4, right. So clearly that sort of matches with our intuition that the B of I is just going I elements offset from the starting location and then picking up whatever value is there. So in other words, it is actually picking up the values in the array A. Now at the same time you can also see that A of 0, A of 1, A of 2 and A of 3 are printed out as expected. What happens to A of 4? It says it is 0, right. I am not sure why. A of 5 also has a value 0. A of 6 has some strange negative number that we have over here, which I have no idea where that came from, and so does A of 7, right. And the bottom line is we cannot know for sure what these values are going to be, right, and in fact if I run the values, you can see, run it again, you can see that these numbers have changed, right. Every time you run it, the numbers printed out for A of 6 and A of 7 are going to change. A of 4 and A of 5 seem to be consistently 0, but that is not something you can rely on. One of the reasons why this comes out to be 0 is because that depends on how exactly the stack frame corresponding to this function demo access bounds has been created, where the different values have been initialized, right, and what exactly was loaded into memory when we jumped into this function and started executing code, right. So it looks as though in this particular case at least those first two integers A of 4 and A of 5 are most likely going to be 0, but it is not something you can count on. The language does not guarantee it. That is important to understand. And as you can see, A of 6 and A of 7 are just accessing some locations completely outside of the and that have nothing to do with anything else that has been printed over here, right. Let us sort of change this around slightly, right, and go in another direction. After all, this is a for loop, so I could potentially also go from -4 to 4. What does that mean? It basically means that I am going to start from a negative value of the offset, right, and go -4, -3, -2, -1, 0, 1, 2 and 3, right. So first things first, the for loop itself is fine. I can actually have a for loop like this. This hopefully should be clear to all of you exactly what is happening over here. You just initialize with something and you move forward from there. But what does B of -4 mean? All that it says over here is go backwards, right. So in other words, this location 2076 would correspond to B of -1 and so on up to B of -4, okay. Let us try it and see what happens, right. And what we find is that B of -4 corresponds to a value -1 because like we said, we do not know what is there. This is outside the range of what we have. B of -3 also is some junk, B of -2 is something unknown, B of -1 happens to be 0. Then we have b of 0, b of 1, b of 2 and b of 3, which are the values 5, 6, 7, 8 that we expect. But now let's look at a. A of minus 4 has the value 5. Why is that? Because a of minus 4 corresponds to b of 0, right? It is 4 integers before the location pointed to by a. So this is not a coincidence, the fact that a of minus 4 reports 5. At least on x86 based processors, a of minus 4 should always give you the result 5. But like I said, if you run this on an ARM based processor, chances are you will get a different result, or it might even crash, right? But in this case, a of minus 3 is the value 6, a of minus 2 is 7, which is basically b of 2, a of minus 1 has the value 8, which is b of 3, right? And then a of 0 goes to 1, a of 1 goes to 2 and so on, okay. So it is possible to go out of bounds on either side of an array. You can either go forwards or you can go backwards. All that you need to think about is, I have a starting location, I have an offset. The offset could be in the positive direction, which means increasing addresses, or negative direction, decreasing addresses, right. How much does one increment in the offset mean? That depends on the data type. If it is an integer, it is 4 bytes. If it is a character, it is 1 byte. If it is a short, it is 2 bytes. Okay. And based on that, we can basically go to the appropriate memory location, retrieve as many bytes as needed for the data type that we have, and interpret it and print it out. That is exactly what the compiler is doing.